All right, welcome everyone to the first part of a really interesting deep dive. And actually, this one was requested by you, the listeners. You want us to dig into the core of good programming style, how to write code that's clean, maintainable, and, just makes everyone happier, including yourself a few months down the line.
You got it. And to get to the bottom of this, we're going to explore this awesome resource, the Ada Style Guide / programming practices over on Wikibooks.
Yeah,
And the cool thing is that even if you don't work with Ada on a daily basis, the principles in this guide are surprisingly universal.
right.
So over these 3 parts, we're going to try to extract the most valuable and practical recommendations, those insightful aha moments that can really elevate your coding game no matter what language you're using.
Absolutely. Think of this as like a cheat sheet to writing code that not only works and works flawlessly, but is also easy for others to understand and modify. Even your future self will thank you. So in this first part, we're laying the groundwork, focusing on 3 key areas. Those sneaky little optional syntax elements that can make a big difference, the art of crafting clear and concise parameter lists, and then the often overlooked power of good type design.
Perfect.
So, ready to dive in?
Let's do it.
Let's start with those often overlooked optional syntax elements that the guide highlights.
Yeah, so what I find really interesting right off the bat is that the guide emphasizes that even though certain syntax elements are, strictly speaking, not required by the compiler, choosing to use them strategically can make a huge difference in how readable and understandable your code is. It's all about making the structure jump out at you.
It makes sense. Like one example that comes to mind is loop names.
Yeah,
We all write loops, but the guide really stresses how beneficial it is to actually name them, especially when you're dealing with nested loops or any loop that has an exit statement in it. I can't tell you how many times I've stared at a wall of nested loops trying to figure out which end goes with which do or for.
right. And the recommendation here is super clear. Associate names with any loop that's nested inside another, and with any loop that uses that exit statement to jump out.
Yeah.
And they even give a nice example with nested loops called process each page. And within it, process all the lines on this page.
I like that.
And they both have these nice, clear labels at the beginning. And the end loop statements also include those names.
Right.
And they even have a simpler loop called look for sentinel value.
Yeah. And it seems so basic, right? But when you stop and think about the why behind it, it's super powerful. Just giving your loops these descriptive names, especially the nested ones, instantly clarifies the code's structure.
Oh, yeah.
Like it's much easier to quickly scan through and see which end matches up with which loop. And in longer functions, especially more complex ones, this can be a huge time saver and it cuts down on that mental clutter. And a well-chosen name can even replace a comment, right? It's like built-in documentation. And if you're ever modifying the code later on, having those explicit names on your exit statements avoids any ambiguity about where you're jumping to.
Exactly. And if you zoom out and think about the bigger picture of code maintainability, it's all about minimizing how much stuff programmers have to keep track of in their heads at once.
Right.
The easier it is to grasp the structure and purpose of a code block, like a loop or whatever, the less likely someone is to introduce bugs when they come back and change it.
It makes total sense. And it's actually the same underlying idea behind the recommendation to name your blocks, right?
Yeah.
The guide suggests using that declared in block name and block name structure, especially for blocks that are nested within each other.
Right. Like the example they give is a trip block. And then nested inside that, you've got blocks like arrive airport, visit customer, departure preparation.
It makes so much sense.
And they're each clearly marked at the begin and the end.
Think about how much easier it is to follow the logic of that entire trip block when each step has its own name. It's like instead of just a bunch of begin and end keywords, you've got these semantic labels that tell you what's going on in each section.
Exactly.
It's all about making the code speak for itself.
Yeah.
And just like with loops, these block names become signposts, making it way easier to navigate and understand the overall structure, especially in larger algorithms.
Yeah, it's like leaving breadcrumbs so you don't get lost in the maze of begin and end statements.
Exactly. All right, so this leads us to how to handle exit statements, especially within those nested loop scenarios we've been talking about. And the guide is pretty strict here.
Yeah.
It says to always use the name of the loop you're exiting from on all your exit statements when you're working with nested loops. No more implicit jumping.
Right, because an exit, when you think about it, is really a jump in your code's execution, kind of like an implicit go-to. So by explicitly stating where you're jumping to, the name of the loop you want to exit,
Yeah.
you make the flow of control much more transparent. There's no more guessing about which loop you're breaking out of. And from a maintenance standpoint, it adds this extra layer of robustness.
Right.
Because if the nesting structure of your loops ever changes, your exit statements stay clear and unambiguous, which reduces the chance of introducing sneaky bugs.
So instead of just saying exit, you're being explicit and saying something like exit process each page.
Right.
So there's no doubt about where the program is going to go next. And it's a small change, but can prevent a lot of confusion, especially when you're debugging or trying to understand someone else's code or even your own code from 6 months ago.
Yeah, for sure. So the last thing in this optional syntax section, the guide really emphasizes consistency when it comes to naming the end statements of your program units.
Right. The guideline says to always include the defining name at the end of things like package and task specifications and bodies, except statements, which are ADA-specific for concurrency, subprogram bodies, and protected unit declarations, another ADA concurrency thing.
And they have this really neat example that illustrates this perfectly. You see it for a package autopilot, a task course monitor, where a task is like a lightweight concurrent unit in ADA.
Yeah.
And they have functions like isEngaged, procedures like engage, disengage, then an except reset within the task body course monitor, and lastly, the end autopilot. So that consistent repetition just reinforces the structure and scope of each unit.
It's like a bookend, right?
Yeah.
It clearly marks the beginning and the end with that same label. And this consistency creates a visual anchor in your code. Especially for larger chunks of code or code with lots of nesting, it's super helpful to verify you've closed everything up correctly and to easily jump to the end of a specific section.
It's a simple practice, but it adds a surprising amount of clarity, especially when you're working with big code bases.
I totally agree. All right, let's shift gears a bit and talk about something equally important for clear code. Parameter lists. And the guide makes a good point when it says that the parameter list is the interface to any subprogram or entry point. And being clear here is absolutely essential for anyone who's using or implementing that code.
For sure.
So first up, let's consider the formal parameters themselves, the names that you give to the inputs and outputs of your functions and procedures. And the guideline here is simple, but super effective. Name your formal parameters in a way that's descriptive enough that you don't need extra comments to explain what they're for.
Exactly. And the example they give is perfect. Imagine you have a procedure called listmanager.insert.
Right.
And if the parameters are named element, into list, and at position, the call basically reads like a sentence. Insert this element into this list at this position.
Right.
So much clearer than if they were just called like X, Y, and Z, which would force you to look up the procedure definition to figure out what each argument means.
Yeah, and that descriptive naming style has a ripple effect, too.
It does.
Not only does it make the point where you call the subprogram easier to understand, but it also makes the code inside the subprogram's body more readable.
Right.
Because if the names clearly tell you what they do, you don't need to keep going back to the declaration or rely on comments to remember what each variable represents. It just lightens the mental load all around.
Absolutely.
Huh.
And then the next thing the guide dives into is named association, which is when you explicitly state which value you're passing corresponds to which formal parameter name when you're actually calling a subprogram.
Okay.
And they suggest using name parameter association in a few specific situations. For subprograms or entry points that aren't used super often, so the reader might not remember the parameter order right away. For those that have a ton of formal parameters, when the parameter you're passing is a literal value or a more complex expression where its purpose might not be immediately obvious, and when you're passing a non-default value to an optional parameter.
Okay.
And even when you're instantiating generic units, the guide suggests using it for subprograms that are called from fewer than 5 places or have more than 2 formal parameters.
Right.
And the example they show is a call to encode telemetry packet, where each parameter is specifically named, like source, power electronics, content temperature, destination ground station, and so on.
Yeah.
So there's absolutely no confusion about which piece of data is being assigned to which parameter in the function.
The benefits here are pretty clear. For less common subprograms, named association acts like inline documentation right at the call site. It tells you exactly what each value represents, and it makes maintenance way easier. If the order of parameters in the subprogram definition ever changes, or if new parameters are added, those calls that use named association are a lot less likely to break as long as the parameter names stay the same. You can even skip over optional parameters by simply not including them in the named association.
Right. And speaking of optional parameters, the
Yeah.
guide does have this nice little caveat that for really simple and super common subprograms like a swap A-B procedure,
Yeah.
always using named association might actually make the code less readable in those specific cases
Mhm.
because everyone knows what those functions do.
Yeah.
It's all about finding that right balance.
Yeah, it's all about picking the right tool for the job.
Exactly.
And one thing to keep in mind is that if you do decide to go all in on named association, remember that if you ever change the name of a formal parameter in the subprogram's definition, you'll have to go back and update all the calls that are using that old name.
Right.
So choosing good descriptive names from the beginning is still crucial.
Absolutely. So moving on, let's talk about default parameters.
Okay.
This is a really powerful feature for making some of your parameters optional by giving them a predefined value if the caller doesn't give one explicitly.
Right.
And the guide suggests using these default values for those occasional specialized uses of subprograms or entry points that are usually called with the same common values.
Yeah.
They also recommend putting these default parameters at the end of the parameter list, and they suggest thinking about adding defaults to new parameters when you're updating existing subprograms.
It makes sense. So the idea is to simplify those most common use cases. If a parameter usually has a certain value, making that the default means people only have to explicitly provide a value when they need something different.
Exactly.
And putting defaults at the end lets people still use positional association for the main and non-optional parameters if they want to. And like you said, adding defaults to new parameters during maintenance is a smart way to add functionality without breaking existing code that doesn't need the new parameter.
Right. It's a way to offer flexibility without forcing everyone to provide all the parameters every single time.
Yeah.
But the guide does have this really important warning here. Don't overuse default parameters, especially if the new feature you're trying to add is fundamentally different from what the subprogram was originally designed for.
Right.
In those situations, it's usually cleaner to just create a separate new subprogram with a more specific interface.
Yeah.
You don't want one function doing a bunch of completely different things based on which optional parameter is being used.
Right, because overloading a single subprogram with too many optional behaviors can actually make the code harder to understand.
It can.
It's harder to see what the function is actually supposed to be doing.
Exactly. So the last thing in parameter lists, the guide is really big on explicitly stating the mode of parameter flow.
Okay.
The guideline is super clear. Show the mode, whether it's in-out or in-out, for every single parameter in your procedures and entry points.
Right.
And really importantly, use the most restrictive mode that accurately shows how the parameter is being used in the subprogram.
Yeah.
So for example, they have procedure open file,
Okay.
and the parameters are file name in string,
Yeah.
open status, the out status codes.
Gotcha.
And another one is entry acquire
Okay.
with key incapability, resource out tape drive.
Right.
And even though in's the default, if you don't specify anything, writing it out explicitly makes it much easier to read and understand the intent.
Right, because by explicitly saying the mode, it's like a contract, right?
Yeah.
It immediately tells anyone reading the code whether a parameter is meant to pass information into the subprogram, receive information back out, or both.
Exactly.
And sticking to the most restrictive mode, for example, if a parameter is only ever read and never modified within the subprogram, not only makes things clearer, but also can help the compiler do better checks and maybe even optimize your code. It also prevents accidental modifications to in parameters.
Right.
Now, there's this interesting exception that they mention, and it's about situations where you might choose to use in-out even if the parameter itself isn't directly being changed, just to give you more flexibility behind the scenes with the implementation.
Right. Like if you're implementing something like a bounded stack, using a pointer to an array, you might declare the stack parameter as in out, even though the pointer itself isn't being reassigned within the procedure.
Yeah.
And this allows for future tweaks or changes to how the stack is represented internally without having to change the interface of the procedure itself.
Right.
But these kinds of exceptions should be carefully thought out and well documented.
Absolutely. All right, so we've covered a lot with optional syntax and parameter lists. And now let's move on to another crucial aspect of writing code that's robust and maintainable. using types strategically.
Yeah.
And the guide really emphasizes how important strong typing is for building reliable software.
It is. And what I think is really insightful is how the guide pushes us to go beyond those built-in primitive types and actually create new types and subtypes based on the existing ones.
Right.
This adds semantic meaning to our data and lets us enforce constraints at the type level.
Exactly. The guideline is to use derived types and subtypes, both to create types that clearly represent different concepts in your problem domain, and also to restrict the range of values that a variable of a particular type can hold.
Right. So like the example they show is type telephone directory is new table and type department inventory is new table. Even though both are based on the underlying table type, they're now treated as totally separate types by the compiler. So this prevents you from accidentally doing things that make sense for one but not the other, catching those potential logic errors early on.
Right.
They also show another example with subtypes where like listing paper is defined as a subtype of a more general columns type, but maybe with a limited range of valid column values.
Gotcha. And the benefits here are huge. By using derived types and subtypes, you're making the intent behind your variables much clearer.
Oh, yeah.
It just makes the code easier to read and understand. And on top of that, it lets the compiler do much more rigorous type checking, catching those potential errors at compile time before they can actually cause problems in a running system.
Right.
The guide even points out how this can help you avoid using those clunky flag variables and manual type conversions, which leads to cleaner and safer code.
Absolutely. If you think about how we model our problem domain in code, using derived types and subtypes lets us create a much more accurate and expressive representation of those real-world entities and their constraints.
Yeah.
It improves the overall abstraction and makes the code easier to reason about.
Makes sense. And the guide also briefly mentions the difference between type derivation and type extension. Derivation, as we've been talking about, creates a new type with the same structure and operations, but as a distinct entity.
Right.
Extension, which is specific to Ada's tagged records, which is like a form of object-oriented type, allows you to not only inherit structure and operations, but also add new data components.
Exactly. Now, let's move on to something the guide strongly advises against in most cases.
Yeah.
And that's the use of anonymous types. These are types that are defined right within a variable declaration without being given an explicit name.
Okay.
And the guideline here is pretty clear. Avoid anonymous types.
Yeah.
Unless you have a really unique data structure where you're absolutely sure you won't ever need to reuse the type definition.
Oh, right.
And they have this contrast between the preferred way, explicitly declaring type buffer index is range 180, type buffer is array, buffer index of character, input line buffer compared to the anonymous version, input line array, buffer index of character. And even though the second one might seem a bit shorter at first, it can cause problems down the road.
Yeah, the reasoning behind avoiding anonymous types is pretty convincing. They're not very reusable. If you declare another variable with the exact same anonymous type definition, the compiler often sees it as a completely different type.
It does.
Which makes it hard to do things like pass them as arguments to the same subprogram, unless it's an unconstrained array in some languages. This really limits code refactoring and the creation of reusable components. It can also make it a lot harder to add new subprograms that operate on these types.
Right. So while that initial shortness of an anonymous type might seem appealing, it often comes at the cost of less flexibility, less reusability, and more difficult maintenance down the line.
Right.
It's generally a good idea to give your types explicit names.
Absolutely. Now let's dive into the concept of private types, which is central to the idea of information hiding and building modular, robust systems.
Right. And here, the guide outlines a hierarchy of preference.
Yeah.
If you need resource management, derive from controlled types. If you need tight control over operations, go with limited private types, then just plain private types. And as a last resort, non-private types. The key idea is to explicitly export only the operations that are absolutely necessary rather than just loosening the restrictions on the type itself.
Right.
So they give an example of a package telemetry that defines type frame header is new ADA, finalization controllable private, and type frame data is private. And the actual details of those types are only revealed in the private part of the package.
I see.
So the main point of private types is encapsulation. You're hiding the internal details of how a data structure is implemented and controlling how it can be accessed and changed through a well-defined set of public operations.
Right.
This makes maintenance so much easier because you can change the underlying implementation of the type without breaking code that depends on it, as long as you keep the public interface the same.
Right.
Limited private types take this even further by only allowing the operations that you specifically define. And controlled types, like in that FrameFitter example, let you manage resources that are associated with the type, like dynamic memory, through procedures like adjust and finalize.
It's like creating a clear boundary between what something does, the interface, and how it actually works, the implementation. This makes your code more adaptable to change and easier to understand and think about at a higher level.
Exactly. And the guide does mention a potential limitation. Some predefined I/O packages might not be able to handle limited private types directly as generic parameters because of their restricted nature.
Right. And lastly, in our discussion of types for this part, we should touch on subprogram access types, which are basically variables that can hold references to subprograms like functions or procedures.
Right.
The guidelines suggest using these subprogram access types when you need to make indirect calls to subprograms. So, for example, you could pass a function as an argument to another function.
Yeah.
But they also recommend looking into abstract tag types and dispatching, which are object-oriented features in Ada, as a more structured and often better approach for dynamically choosing which subprogram to use, especially in object-oriented scenarios.
Right. And they give this example of a generic package, generic integration,
Okay.
which defines type integrand as access function, X flow type, return flow type, and then a procedure try estimate that uses residue access to pass a specific function as a parameter to the integrate function.
Mm-hmm.
This allows for a really flexible and dynamic program design.
Right.
But, as the guide points out, for situations where you're working with polymorphism and object-oriented principles, using tag types and dispatching often leads to a cleaner and more maintainable design pattern.
So in this first part of our deep dive into the Ada style guide, we've really unpacked some fundamental principles for writing better code.
Yeah, we have.
We've talked about how paying attention to those optional syntax elements, designing our parameter lists carefully, and thoughtfully using the type system can all contribute to writing code that not only works, but is also much clearer, easier to maintain, and less error-prone.
Absolutely. We've looked at specific recommendations from the guide and the reasoning behind them, and hopefully this has given you some practical takeaways that you can apply in your own coding, no matter what languages you're working with.
Totally. And this is just the start. In the next part of our series, we're going to dive into what the guide says about data structures and expressions.
Right.
We'll be uncovering even more valuable advice from this awesome resource.
Looking forward to it.
So if this deep dive has sparked your curiosity, or if you have any questions, we encourage you to go check out the Ada Style Guide / Programming Practices over on Wikibooks. It's a treasure trove of information.
It is.
And make sure to join us for the next part of this deep dive. We're going to keep pulling out those golden nuggets of knowledge to help you become an even better programmer. We can't wait to have you back.
See you then.
See you then.